Hello there, this is Max again, and today I will tell you all about the statue in Rome problem, where we had some marble with some salt in it. At the left top corner I've drawn this cylindrical marble piece with thickness D and a variable concentration of the salt over time. The concentration of salt at the outside was always 0 kilograms per square meters. And what happens is that the salt will diffuse to the outside. The marble will be laying 400 days in the water, and the thickness of the marble piece was 0.15 meters. 1% salt was left after those 400 days. Now, there was told that you could make use of the permeation theory. That means that we are using long timescales. Now, you had to calculate Fourier's number for this situation. First thing you have to do then is to take the average M, which looks like this. Why the average one? Because also an average salt concentration was given, and therefore this is the only one you may find useful to use. And you have to fill in those boundary conditions, just as like with the quenching question, only now for concentrations. And you are allowed to do this in percentage. This will make no difference at all. So C0 means the concentration at the beginning, so this is 100%. C1 is the concentration at the boundary, which is 0 because this is the water and there is no salt in it. And the average C is 0.01%, 1%, because this is still left. If we fill this all in, we can find average M, which is then 0.01. We can then look in the graphs for cylindrical coordinates and you can find Fourier's number. In this case it was 0.18 without any units. Then the next objective was to find the diffusion constant for salt inside the marble piece. You can write Fourier's numbers as the diffusion constant times time divided by d squared. This is one you have already seen if it's correct. Also, when you're doing this for heat transfer, the d will be replaced by the heat diffusivity, A, but not for now. I can rewrite this equation to diffusion constant is Fourier's number times d squared over t, and I can find, if I fill in all the numbers, which I have, is that the outcome is this one. The next question was whether the assumption that was made was correct. The assumption was that this process was completely controlled by diffusion inside the marble and not of salt going out of the marble, which is here represented by K. We can check whether this assumption is valid by looking at the resistance of those processes. When we take a look at the resistance, 1 over K is the resistance for the salt going out of the marble, and X over D is the resistance for the salt in the diffusion process inside the marble. And if you take a look at both those values, you don't have to calculate them exactly, because you can see immediately that 1 over K is way smaller than X over D. And therefore the resistance inside the marble is way larger. And when the resistance is way larger, it will take a longer time to diffuse, so those timescales are way longer. Therefore, this is a mainly diffusion control process. The next question was to determine the time inside a sphere. Now this was exactly the same situation, only for another geometry. So first determine M at the same way as you did for the cylinder. Then you can read out VA's number, only this time you have to read out a different line since you now have a sphere geometry. When you have VA's number, you can use the equation for VA again, and that was this one, only now rewrite it for the time and then fill in the numbers, and then you have the time it takes to do this. Then we went the other way around. So we know the time, but we want to know the concentration at the inside. So in the center of this sphere, we know VA's number from last exercise, which was 0.105. We can look into the graph again, this time the other graph, since you're not looking at average concentrations, but at the maximum concentrations. And then we'll find M, which was 0.03. It can be that you have a slightly different number, since reading out graphs is not perfectly exact, but it should be around this value. You can use also the formula again, only now with maximum concentrations, which looks like this. Fill in the numbers, it's the same numbers as these ones, only now you want to find the maximum one, so then you can find it 0 minus C. Now just reorder, and you can see that this is 3%. And this was the number we were looking for. I hope you understand what I just explained. If not, don't be afraid to ask us in the forum. See you, and good luck with your graded questions.